Hello, let's see you again, and let's start our lecture on avionics engineering. Okay, today we have lecture number 18, and the topic of this lecture is a flight management system. Flight management systems, or simply FMS, has become one of the key avionics systems because because of the major reduction in pilot workload, which is achieved by its use. In the case of military aircraft, they have enabled single crew operation of advanced strike aircraft. Flight management systems started to come into use in the mid-90s, 80s, last century, and are now in a very wide scale use, ranging from relatively basic systems in commuter type aircraft to all single all dancing systems in long range wide body jet airline. They have enabled two crew operation of the largest civil airplane and are generally a dual FMS flight management system installation because of their importance. This slide is a block diagram of a typical flight management system. The benefits they confer are briefly set out as the quantifiable economic benefit. This means provision of automatic navigation and flight path guidance to optimize the aircraft's performance and hence minimize flight costs. Air traffic, it means growth of air traffic density and consequently more stringent ATC requirements, particularly the importance of 4D navigation. Accurate navigation sources means availability of accurate navigation source. For example, it may be INS or IRR, GPS, VOR, DME, and ILS or MLS, computing power. In this case, availability of very powerful, reliable, and affordable computers. Data bus system means ability to interconnect the various subsystems. You know, the FMS carried out the following tasks. First, flight guidance and lateral and vertical control of the aircraft flight path. Second, monitoring the aircraft flight envelope and computing the optimum speed for each phase of the flight, and ensuring safe margins are maintained with respect to the minimum and maximum speeds over the flight envelope. And third, automatic control of the engine thrust to control the aircraft speed. In addition, the FMS pilot, FMS, not pilot, the FMS plays a major role in the flight planning task, provide a computerized flight planning aid to the pilot, and enables major revisions to the flight plan to be made in flight if necessary to cope with changes in circumstances. And namely, this slide shows the flight management system architecture of a modern airline. In this case, the Airbus A380. Two independent flight management systems FMS1 on the captain side and FMS2 on the first officer side carry out the flight management function. The cockpit interfaces to the flight crew provided by each FMS comprise a navigation display. Here it means at the ND navigation display, a primary flight display PFD, a multifunction display MFD, a keyboard and cursor control unit KCCU, and electronic flight instrument KCCU and electronic flight instrument system and control panel. The multifunction display MFD, displays textual data. Over 50 FMS pages provide information on the flight plan, aircraft position, and flight performance. The multifunctional display MFD is interactive. The flight crew can navigate through the pages and can consult, enter or modify the data via the keyboard and cursor control unit KCCU, cursor control unit KCCU. The keyboard and cursor control unit enables the flight crew to navigate through the FMS pages on the MFD and enter and even modify data on the MFD, as mentioned a bit earlier. I hope you remember, right? And all that can also perform some flight plan revision on the lateral navigation display ND. The EFIS control panel, provides the means for the flight crew to control the graphical and textual FMS data that appear on the ND and PFD. There are 3 flight management computers: FMS-A, FMC, flight management computer A, B, and C, to carry out the functional computation, which can be reconfigured to maintain the system operation in the event of failure. And there are 3 different FMS operating modes. It means dual mode, independent mode, and single mode dependent on the system status. Let's start with the dual mode. Both flight management systems, FMS1 and FMS2, are healthy. And this figure shows the configuration in normal operation in the left side illustration, and the configuration of the single flight management computer failure, which you can see in the right side illustration. In normal operation, FMS-A provides data to FMS-1, FMC-B provides data to FMC-2 and FMC-C in the standby computer. Of the 2 active computers, the FMC is the master, and the other is the slave, depending on which autopilot is active and the selected position of the FMS source select switch. The 2 active FMC independently calculate data and exchange, compare, and synchronize these data. The standby computer does not perform any calculation, but is regularly updated by the master FMC. In the case of a simple FMC failure, for example, FMC-A, FMC-C provides data to FMS-1, as shown in the right side illustration in this figure. Okay? Independent mode. In the independent mode, FMS-1 and FMS-2 are both operative, but there is no data exchange between them because they disagree on one or more items such as aircraft position, gross weight, etc. This case is shown in the left side illustration in this figure. Next, single mode. The loss of two FMCs causes the loss of either FMS1 or FMS2. The data from the operating FMS is displayed to the flight crew by operating the source select switch. This case is shown in the right side illustration in this figure. Radio navigation tuning. The FMS automatically tunes the radio navigation aids used for the radio position computation. The NAWA is for display on the navigation display, and the landing system NAWA aids in dual and independent modes for each FMS tunes its on-site NAWA aid. This comprises, in the case of the A380, one VOR for DMEs, one ILS, or maybe MLS or GLS optimal, and one ADF optimal. In single FMS mode, or in the case of a communications failure between an FMS and its outside radio management panel, RMP, the available FMS will tune the NAWA on both sides. The tuning on the on-side NAWA passes through the on-side RMP, RMP1 or RMP2. The A380 FMS radio navigation tuning system is shown in this figure together with the position and NAWA page displayed on the multifunctional display. The NAWA is displayed on the navigation displays and the landing system NAWA, which can also be tuned manually on the position NAWA page on the MFG or the radio management panel. Manual tuning always gets priority over automatic tuning. Navigation. The FMS combines the data from the navigational sources, comprising the inertial system, GPS, and the radio navigation systems in a Kalman filter to derive the best estimate of the aircraft position. The accuracy of this estimate is also evaluated. This slide is a block diagram of the Kalman filtering of the navigation sources. Each FMS computes the aircraft position and the position accuracy. The FMS computed position is an optimum combination of the inertial position and the GPS or radio position, depending on which equipment provides the most accurate data. This results in 4 navigation modes in decreasing order of priority. First, inertial IRC or GPS, inertial IRS or DME and DME, inertial IRIS, BOR, DME, and inertial IRS only. The FMS aircraft position always uses the inertial position. This computation is not possible if the inertial position is not valid. And in this case, all the FMS navigation and flight planning functions are no longer available. The FMS continually computes the estimated position navigation performance, RNP, to define the aircraft navigation accuracy. The FMS continuously compares the actual EPU with the current R&T and define the navigation class as high if the EPU is less than or even equal to the R&T, or low if the EPU is greater than the R&T. The navigation class has to satisfy the airworthiness authorities' accuracy requirements. The FMS computes ground speed, track, wind direction, and velocity. It should be noted that the air data system provides the high information for vertical navigation. As stated a bit earlier, the FMS provides both lateral and vertical guidance signals to the autopilot to control the aircraft flight path. In the lateral case, the FMS computes the aircraft position relative to the flight plan and the lateral guidance signal to capture and track the flight path specified by the flight plan. Three-dimensional vertical guidance is provided to control the vertical flight profile, including the time dimensions, as will be explained in more detail a bit later. This is our particular benefit during the descent and approach. Let's start with the flight planning. As explained a bit earlier, a major function of an FMS is to help the flight crew with flight planning, and it contains a database of radio naives, VOR, DME, PORTAC, TACAN, NDB, comprising identification, latitude and longitude, altitude frequency, magnetic variation, class, airline figure of merit. Waypoints, usually beacons, airways, it means identifier, sequence number, waypoints, magnetic core. Airports means identifier, latitude, longitude, elevation, alternative airport. Runway, in this case, means length, heading, elevation, latitude, and longitude. Airport producer, ICAO code, type, SID, star, ILS, profile descent. Company routes means original airport, destination airport, route number, type, cruise altitudes, cost index. The navigation database is updated every 28 days according to the ICAO cycle and is held in non-volatile memory. Now, it is clearly essential to maintain the recency and quality of the database, and the operator is responsible for the detailed contents of the database, which is to ARINC 424 form. This figure illustrates a typical airline route section and shows the information content. The flight crew can enter the flight plan in the FMS, including all the necessary data for the intended lateral and vertical trajectory. When all the necessary data is entered, the FMS computes and displays the speed, altitude, time, and fuel predictions that are associated with the flight plan. The flight crew can change the flight plan at any time. A change to the lateral plan is called a lateral revision, and a change to the vertical plan called vertical revision. The FMS can simultaneously memorize 4 flight plans. First, one active flight plan for lateral and vertical long-term guidance, and for radio navigation auto-tuning, and three secondary flight plans with drafts to compare prediction, to anticipate a diversion or to stop company, ATC, and onboard information system flight plan. The lateral flight plan includes the departure, cruise, and arrival, and even a components or waypoints that are linked with the flight plan legs and transitions between legs. Next figure shows the displays on the MFD of the active initialization page, active init, and active fuel page, or simply active fuel. This ease and visibility of the data entry process can be appreciated. A flight plan can be created in three ways. First, by inserting an original or destination pair, and then manually selecting the departure, waypoint, airways, and arrival. Second, by inserting a company route stored in the database. Third, by sending a company request to the ground for an active flight plan, F-plan, uplink. The flight crew can perform the following lateral revision. First, delete an itself waypoint. Second, departure procedure, takeoff runway, standard instrument departure, SID, and transition. Third, arrival procedure, like runway, type of approach, standard terminal arrival route, via transition. And fourth, airway segment. The flight crew can also perform the following vertical revisions. Time constraints, speed constraints, constant Mach segments, altitude constraints, step altitudes, and wind. This figure illustrates the active flight plan page displayed on the MFD for carrying out flight plan revision. Next subtopic today's lecture, performance prediction and flight path optimization. The FMS is available to optimize specific aspects of the flight plan from a knowledge of the aircraft type, weight, engine, and performance characteristics, information on the wind and air temperature, and the aircraft state, like airspeed, Mach number, height, and etc. The FMS continually monitoring the aircraft envelope and ensures that the speed envelope restrictions are not breached. It also computes the optimum speed for the various phases of the flight profile. This is carried out considering factors such as aircraft weight, means computed from a knowledge of the takeoff weight and the fuel consumed, measured by the engine flow meter. It should be noted that fuel can account for over 50% of the aircraft weight and takeoff. Central gravity position, computed from known aircraft loading and fuel consumed. Flight level and flight plan constraint, wind and temperature model, and company route cost index. The recommended cruise altitude and the maximum altitude are also computed from the above information. The flight crew enter the following data to enable the performance computations and flight plan predictions to be made. Zero fuel weight, ZFW, and zero fuel center of gravity, block fuel, airplane cost index, CI, flight conditions, cruise flight level, CRVL, and temperature, and block fuel, airline cost index, CI, and flight conditions, with temperature. The FMS computes the following predictions from the flight plan and the flight crew data entries, like wind and temperature, speed changes, waypoint computation. For each type waypoint, observe the waypoint, like distance, estimated time of arrival, speed, altitude, estimate fuel on board. Wind for each waypoint, observe the waypoint. For primary and alternate destination, ETA, distance of destination, EFOB at destination. These predictions are continually updated depending on revisions to the lateral and vertical flight plan, current wind and temperature, actual position versus lateral and vertical flight plan, and current guidance mode. The prediction and the lateral flight plan combine to form a vertical profile that has 6 flight phases. The multifunctional display page display used to carry out the performance calculation. An optimization process is shown, which is shown in this figure. Flight envelope protection is achieved by computing maximum and minimum selectable speed, stall warning, low energy threshold, alpha flow signal, and reactive wind shear detection. The FMS also computes maneuvering speed and flap and slat retraction speed. This figure shows these limits displayed on the primary flight display. Next sub-question today's lecture, control of the vertical flight path profile. The FMS selects the speeds, altitude, and engine power settings during climbs, cruise, and descent considering the flight plan, the prevailing conditions, and the optimization of the operation of the aircraft. The vertical definition of a typical flight plan is shown in this slide. The task which can be carried out and the facilities provided by the FMS during the various phases of the flight are briefly summarized as the next. First, it means every flight starts with takeoff. This is the critical speeds V1, VR, and V2 are inserted by the crew and displayed on the primary flight display. Second, climb. The FMS uses the manually input speed, the ATC constraint speed, or the economical speed. It determines the start of the climb during takeoff and predicts the end of the climb and the optimum cruising flight level. Next, cruise means 5 flight levels can be defined manually in the FMS. 2 flight levels can be stored for every route in the navigation database. During the cruise, ATC or the crew may change the cruise altitude, and the FMS can perform a step climb at economical speed, or a step descent and 1,000 feet per minute at an economical speed too. These events are also displayed symbolically on the navigation display. Descent, the FMS uses the manually input speed, the ATC constraint speed, or the economic speed. The altitude and speed during the descent are computed as a function of the distance to the destination, and a geometric profile is formed. The flight path is then computed backwards to satisfy the constraint. Approach. The FMS can be can be coupled to the autopilot or alternatively provide guidance information to the pilot for manual control of the aircraft. Speed is critical during this phase, and the approach speed is computed with respect to VREF and the landing configuration like flaps, slots, etc., and the wind at the destination. The approach mode is entered at the end of the descent, and the approach ends either with landing or go around. Lateral guidance is provided by the FMS from the computed aircraft position, and vertical guidance from barometric altitude when an RNAV approach has been selected. The FMS also provides speed control. At the end of the RNAV approach, the crew takes control to carry out the landing using visual references. When an ILS approach has been selected, the FMS tunes the ILS frequency and selects the runway heading as required for the runway selected by the crew. The approach and landing guidance is carried out by the autopilot using the ILS localizer references for horizontal guidance and the ILS glide slope references for the vertical guidance until the glide extension and the flare phases, unless the crew elect to carry out an automatic go around, or elect to take over control. And final, go around. This is always assumed. The FMS manages the climb to the accelerating altitude or a selected altitude and provides track guidance from the outboard bound track defined in the flight plan. The lower selection of the navigation display is known as the vertical display zone and is used to display the vertical flight profile. This slide is an annotated display of the aircraft's flight path in the vertical plane, where the terrain height information is combined with the vertical flight profile to provide a synthetic view of the aircraft's vertical situation. Now, next topic today's lecture, operational modes. The FMS provides a number of very useful operational modes, which are shown in the little sketches in this figure from A to D. First, tangential, to direct the mode. This is shown in figure A on the left upper corner and provides navigation from the current position to any waypoint in the flight plan or enter during the flight. Next, turn anticipation. This is shown on figure B on the left bottom part of the slide and avoids overshooting waypoint. It reduces both the distance flown and the off-track maneuvering. Third, parallel offset tracking. This is illustrated on figure C on the right part of the slide. The lateral offset allows ATC to increase traffic flows in certain cases. And fourth, holding pattern. This is illustrated in figure D on the right bottom part of the slide. The FMS produces a precision holding pattern based on published ICAO entry procedure to reduce the pilot workload. Next topic, 4D flight management. 4D navigation has already been briefly referred to a number of times. In fact, 4D flight management is a better description of the process. 4D flight management covers the optimization of the aircraft's flight along the most conservative 3D paths through climb, cruise, and descent within the constraints of the air traffic control environment. Most importantly, the arrival time of the aircraft is also controlled so that it feeds into the air traffic flow without incurring or causing delays. This is achieved by the automatic closed-loop control exercised by the FMS through the autopilot and auto-throttle system. This controls the aircraft's flight path so that its 3D position at any time corresponds closely with the optimum time reference flight path generated by the FMS computer. When instructed to resume the descent of FMS, then rearranges and guides the aircraft down to the ATC specified position at the pre-established time. The process of automatic 4D descent control is very briefly described a bit recently. An ideal 4D trajectory, which is defined by a table of time, range, and altitude, is pre-computed as briefly explained before this work. So flexibility is essential for a 4D flight management, and there must be several minutes of arrival time variation possible, and so that the arrival time of the aircraft will coincide with the arrival time required by the air traffic controller. Some flexibility is also needed to be compensated for differences between the actual and predicted wind, and for performance modeling discrepancies with the actual aircraft in the FMS computation. Also, these are typically quite small. This figure shows an altitude and range error from the ideal time reference trajectory. The air traffic control system also specifies the arrival time of the aircraft to the nearest integral minute. So the aircraft must have at least 30 seconds of arrival time flexibility to pitch. Delay caused by traffic or weather also requires some flexibility. Besides arrival time flexibility, there must also be some path flexibility. For example, air traffic control may require the aircraft to vector off course because of traffic. The 4D guidance and control exercised by the FMS then automatically rearrange the descent and compute the new course to the position specified by the ground ATC and make good the original or newly specified arrival time. Occasionally, aircraft are required to level off in their descent. For example, when the high-altitude air traffic controller hands the aircraft off to the low-altitude controller for the current aircraft position or current range. The required altitude is computed from the ideal trajectory, and the combination of pitch attitude and direct drag or engine thrust is used to control both the altitude error and the speed. Pitch attitude is controlled through the pitch channel of the autopilot by the FMS to maintain the aircraft on the ideal trajectory or to return to it, while drag or thrust is used to control the speed as necessary. For the current time, the required range is computed and speed changes are effective to control the range error and hence the required time. The FMS exercises speed control for the too low case by engine thrust control through the auto throttle system. The too high or too fast case is controlled by direct drag control by the spoilers or speed breakers. For safety or comfort reasons, the speed brake extensions is generally controlled by the crew in response to a PFD message and not directly by the FMS or autopilot. The arrival time uncertainty with automatic closed-loop 4G guidance and control is typically less than 4 or 8 seconds for 95% of all arrivals, assuming ATC-related errors are zero. The effectiveness of the system can be seen. The corresponding arrival time uncertainty for performing and operating high-profile descent without time control is estimated to be on the order of 40 seconds. the major reduction in arrival time uncertainty together with the ability to provide arrival time flexibility to accommodate delays caused by traffic or weather, etc., coupled with flight path flexibility to meet ATC requirements make 4D flight management a very important advance. I think it's enough for today. Generally, I hope you enjoyed this lecture, and I'm looking forward to seeing you next time to continue studying our favorite course. Bye.